to introduce our first speaker of today, Oli Marti, who will talk about, who will continue his mini course on Blaschke products and inner functions. Please.
Thanks. So let me start just recalling what we did during the last 10 minutes of yesterday. So we had a mapping, a self-mapping of the unit disk and a point in the circle. And then, so here is the point in the circle. And then we were considering the composition of this mapping so that the composition sends the disk to the right half plane. So this means that the composition can be written as the Herlot's integral of a positive measure. And this positive measure is called the Alexandrov-Clark measure of the function f at the point alpha. And taking real parts, what you get is that say the Poisson kernel at the point f of z evaluated at alpha is equal to the Poisson integral, let me write it that way, of mu alpha evaluated at the point z inside the disk. So you have this nice relation. And from this nice relation, which holds for any point z in the disk and any alpha in the circle, we were, making some observations, some remarks. And this was what we did yesterday. We started to do that. So the first thing is, as you see, the first statement is that you can recognize if the function is inner in terms of the Alexandrov-Clark measure. So the function is inner even only if the Alexandrov-Clark measure is singular with respect to Lebesgue measure. So it's concentrated on a set of Lebesgue measure 0. In that case, when the function is inner, you can say even more. You can say that the measure is concentrated in the preimage of the point alpha. So it's something like that. You have here the unit disk, and you have here the point alpha. I'm sorry, I should maybe do it here. So you have here the unit disk, and you have here the point alpha. Then you look to the preimage of the point alpha. This is going to be a set of Lebesgue measure 0, a very tiny set. Which topologically could be very complicated, but still a small set. So this is the preimage of f by the point alpha, of the point alpha. And this is the place, in this tiny set is the place where the Alexandrov-Clark measure is concentrated. Moreover, these measures are mutually singular because they are concentrated in disjoint sets. So they are concentrated in, so if you have another point, say beta here, then the preimage, of course, will be different, will be maybe this set of points. And here is where mu beta is concentrated. Okay. Very good. And you should think on these Alexandrov-Clark measures as measures which give, which in a certain sense, tell the intensity in which the function f takes the value alpha. So actually what happens is that say the biggest is the measure at a given point, the smaller is the derivative of the function at this point. And this can be easily shown in the case of finite Blaschke products. So if you have a finite Blaschke product, then, well, in that case, the computation is very easy, right? Because if you have a finite Blaschke product, then this set is just a finite set, a finite collection of points in the circle. Each point alpha has finally many preimages. So the corresponding Alexandrov-Clark measures, which is concentrated in this set, has to be just a linear combination of point masses. And this is when just using this formula, And an easy computation tells you that the Alexandrov-Clark measure has this form in the case of finite Blaschke products, right? Just this linear combination of Dirac masses located at the pre-images of the point alpha. Okay, so I'm not going to do this computation, and actually we are not going to use it. But I just wanted to remark that, as I said, mu alpha has to do with the intensity in which the function f takes the value alpha. Okay, so here is the main, our main tool. This is Alexandrov disintegration theorem. It's very nice, right? Because it tells you something like that. Let's see. This is the picture we should have in mind. Here you have the point alpha. Here you have the pre-images of the point alpha. And the measure mu alpha is concentrated in these pre-images. As I said, if you have a different point beta, well, the pre-images will be located in other points. For instance, in the case of a finite Blaschke product, this would be the places where mu beta is concentrated. And this happens for any point in the circle. So the Alexandrov disintegration theorem tells you that when you average all these measures, you return to Lebesgue measure. So the situation is as follows. You have a collection, a continuous collection, a non-countable collection of singular measures, the mu alphas, which are mutually singular, and in such a way that when you average them, you return to the Lebesgue measure. So this is really, well, quite a family, right? It's, well, a sophisticated family of measures. Okay, so what does this mean? That when this is what I have said, that when you average them, you return to Lebesgue measure. In practical terms, this means that when you integrate, well, an integrable function against Lebesgue measure, you can think on that in the following way. You first integrate with respect to given Alexandrov-Clark measures, to respect to a given Alexandrov-Clark measure, and the result you integrate with respect to alpha. Okay. So, well, the proof of this is has a delicate point, because first we should prove that whenever you have an integrable function, this quantity makes sense. So you have to show that whenever you have an integrable function, the function g is integrable with respect to the Alexandrov-Clark measure, at least for almost every alpha. And this is the case. But let me just skip this technical point and let me just prove it for g continuous.
Ciao.
And well, when g is continuous, the situation is easier because, as you know, linear combinations of Poisson kernels are uniformly dense in the space of continuous functions. So this means that we can, without a lot of generality, we can assume that g is a Poisson kernel at a given point in the disk. And in that case, the proof is very easy because, well, the left-hand side, this integral, since g is a Poisson kernel, is of course 1. And now let's look to the integral, the double integral in the right, this double integral. Well, first let's compute the interior integral. So let's compute that. Well, g is just the Poisson kernel. Well, our definition of Alexandrov-Clark measures tells that this is just the Poisson kernel of at the point f of z evaluated at the point alpha. So what we need to do is just to compute this, as I said, the interior integral is just the Poisson kernel. So you get the Poisson kernel at the point f of z evaluated at the point alpha. And then you need to integrate over alpha. But this is just the integral of the Poisson kernel at a given point in the disk. So this is also one, right? So this finishes the proof, right? When in the case when G is continuous, because when G is continuous, as I said, you can assume that G is the Poisson kernel. So in that case, this gives you one and this also gives you one. So this is the proof in this particular case, okay? Okay, so this, as you'll see during this talk, this will be our main tool to study, say, stochastic properties of inner functions. So the plan today is to present a version of the central limit theorem for iterates of inner functions. Okay, so let me just recall the central limit theorem, the classical central limit theorem for you. So if you have a sequence of real, independent, identically distributed random variables with mean 0 and say variance sigma squared, then the central limit theorem tells that when you perform this average of the random variables, then the average 10 in distribution to a Gaussian, right? So this means that the probability that this set, this random variable takes value in a given, say, interval. So K is going to be here an interval in the line is just the Gaussian measure, the Gaussian measure of the interval. Okay, the Gaussian measure of the interval. Okay, so this is the probably the most classical version of the central limit theorem, and it has, of course, extended in many directions, in many different directions. In particular, there are versions of the central limit theorem which are natural in function theory. So here is a version, right? The version of the central limit theorem I want to present is a classical result by Sal and Zygmunt on lacunary series. Okay, so a lacunary series is a power series of the following form. Is a power series where the only monomials which are present are monomials which grow exponentially fast. Okay, so for instance, you may take nk to be 2 to the k, right? So this would give you an example of a lacunary series. Well, what happens is that the idea, I guess, behind all these results is that if the series is lacunary, then these monomials, because the exponents grow exponentially, these big monomials behave as independent random variables. And it makes a lot of sense, right? Because, for instance, imagine that n sub k is 2 to the k, right? Imagine you are in that situation. So it makes a lot of sense because even if you have some information on how, which are the values of z to the 2 to the k, then, the values of z to the 2 to the k plus 1, since these grow exponentially, probably not too much information can be captured from z to the 2 to the k. Okay, so now there is a classical result by Paley. So this point match convergence is due to Paley. I forgot to mention that. It's a classical result by Paley, and tell you the following. This very nice result, which is also has some probabilistic flavor. It tells you that whenever you have a lacunary series, then the following conditions are equivalent. Either the series converges at almost every point in the circle, or the series converges at a set of positive measure, or the coefficients are square summable. These three conditions are equivalent. So if you want, in other terms, there is again a dichotomy. It's like a 0-1 law. If the series converges, if the series of the coefficients, if the series of the squares of the coefficients converges absolutely, so if the coefficients are in little L2, then the series converges, the lacunary series converges at almost every point in the circle. However, if the series diverges of the coefficients of the square of the coefficients diverges, so if the coefficients are not in little L2, then the lacunary series diverges at almost every point in the circle. So you have very good behavior or very bad behavior. You do not have intermediate behaviors. Okay. So then it's quite natural to ask, well, what happens when the series diverges? When the series of coefficients are not, when the coefficients are not in L2, you would expect to have some result on the distribution of values of the lacunary series. And this is the central limit theorem, which was proved by Salem and Zygmunt, well, many years ago in 1947. It says the following. So assume that you have coefficients which are not in little L2. Okay, so assume that you have coefficients whose squares are not summable. And then you consider these, say, this plays the role of the variance. So the partial sum of modulus of an squared. And assume that condition, right? So this condition tells you that in this sigma n squared, one individual an is not really important. So sigma n tends to infinity, of course, because the sum tends to infinity, but not due to the growth of a single term in the series. So if this is the case, then what happens is that these quantities, which, as I said, the partial sums would diverge at almost every point. But when you normalize them conveniently, then this tends in distribution to a complex Gaussian now, okay? And this means what I have written here. Right? This means that the measure of the set of points where these partial sums lie in a given disk, so K here is going to be a disk, for instance, in the plane, the measure of the points in the circle where this quantity is in a given disk, this tends, when n tends to infinity, of course, to the complex Gaussian, to the complex, to the, what I want to say is to the Gaussian measure of the disk K, okay? So this, well, this result actually we like a lot, and I guess that also Salem and Zygmunt like it a lot because they proved many different variants of this result. They proved similar results for trigonometric lacunary series. They also proved tail versions of this central limit theorem, and they also proved local versions of this central limit theorem. So let me at least mention the local version. So this is the result they proved, but as I said, they proved more. Actually, they proved the following even nicer result, I guess, that whenever you have a set, so fix a set E in the circle. And instead of looking to the measure of all the points in, so just a measurable set, I'm sorry, of positive measure. So it could be very complicated, okay? And now you look to, instead of looking to that, you look to the measure, to the normalized measure. So you look to these quantities, the measure of the set of points where this lies in a given disk, and you normalize it, you divide by the length by the measure of it. And this thing is still true. So this still holds. So this means that this central limit theorem even holds locally on any set of positive measure. Okay, so, and as I said, they prove many other variants, but I wanted to mention this. Okay, so our main objective today is to prove a similar result for inner functions. Okay, so let's go to that. Well, when you want to prove a central limit theorem for inner functions, the first thing I guess that one should ask is, well, how far away we are from the usual assumptions. So usual assumptions is that our random variables should be independent and identically distributed. In our case, our random variables are not random anymore, but the iterates should take the place of the random variables. Okay, so in a sense, we should ask ourselves if the iterates are independent and if they are identically distributed. And here there is a good news and a bad news. Well, let's start with the bad news. Bad news is that they are not independent. They cannot be independent in any sense, right? Because at the end, the n plus 1 iterate depends on the nth iterate, right? So it's they are clearly not independent. And this will be our main obstacle, right? That they are not independent. However, there is also, as I said, the good news. And the good news is that they are identically distributed. And they are identically distributed because we already show it, we already proved it. This is Leffner's lemma, right? When you have an inner function fixed in the origin, the back measure is invariant. So this holds, right? Let me use this to make a computation. So instead of writing Leffner's lemma in this form, I will use it in this form. So what I mean here is that whenever you have an invariant measure, so for instance, Lebesgue measure, what this formula tells you is that you can, you can decompose. I mean, if you want to compute this integral, you can decompose with f. So you can write this identity. So why this is true? Well, it's very easy, right? So to prove this for any integrable function g, it's enough to prove it for characteristic functions of sets, right? Because such linear combinations are then inner one. So with a lot of generality, we can assume that g is just the characteristic function, the indicator function of a set E in the circle. But in that case, it's the result is just Leffner's lemma, because this is, of course, the measure of E. And this is, of course, decomposed with f will be just the characteristic function of the preimage. So this is just the measure, Lebesgue measure of the preimage. Okay, so this is clearly another restatement of Leffner's lemma, and this is what we are going to use to compute the variance. So to compute the variance, we will need to compute first these integrals you have here, right? So let me start computing these integrals, okay? So here, the first step is the fact that we can, as I said, whenever you have something, a function which depends on f, you can forget about f, right? So of course, this function depends on f to the n, so we are going to apply this Leffner's lemma. So when we apply it, you arrive to this integral, okay? But this integral is just by Cauchy's theorem. This is just the derivative of the iterate at the origin. And now recall that the origin is a fixed point for our inner function f. So you just apply chain rule, and then you arrive to this quantity. Okay. So this is a very easy computation using Leffner's lemma, and this is what is used here, right? This will be our variance. Okay, this will take the place of the variance in the central limit theorem. So the variance is like the L2 norm. Okay, you don't see here the mean, right? Because the mean is 0, because the function f vanishes at the origin. Then what we do is the most naive thing, which is to compute. I mean, we just write this as the sum of an squared fn squared, and then we have the mixed terms, right, which would be just 2 times the real part an, and then I would have something like the sum I guess fk something like that. This is what you have this is what you need to integrate, right? At first sight, it could see as hopeless, but several things help. The first is that the function is inner, right? So this is 1 at almost every point, so we can forget about this. And the second is that we already did the computation of the integrals of these parts, right? And these integrals were giving us, the integrals of these were giving us just f prime of 0 at the point k, right? So what you get is this identity here. And then, well, this you need to check, but it's not hard to check that this is comparable to the sum. I mean, you have here 2 terms, this one and this one. And the idea is that since f is a self-mapping of the disk, which is not an automorphism, this is going to be smaller than 1 in modulus. So this second term is like an error term. It can be absorbed by the first one. So for instance, imagine that the function f vanishes at the origin, and also that the derivative vanishes at the origin. In that case, this second term would disappear. So at the end, what I mean is that the variance is comparable to the L2 sum of the coefficients. Okay. So now we have, using Leffner's lemma, we have already localized the variance. The variance will be this expression here. Okay. And now I can state our result, which is the central limit theorem, which I have in this screen. So here I have recalled the definition of the variance, this large expression here. And then here is our result. Assume that the function is inner, that vanishes at the origin. So the origin is the Denjoy-Wolff fixed point in that case, which is not a rotation. Okay. And assume that the coefficients are uniformly bounded. So this is, well, we can prove this theorem under weaker assumptions on the coefficients an. But for the presentation, I guess this will be enough. Okay. So assume that the coefficients are bounded. And of course, the coefficients are not square summable. Then what happens is, again, that the partial sums, when conveniently normalized, converge in distribution to a complex standard Gaussian. So again, this means, if you want, this means that the measure of the points psi in the circle where these quantities stay in a given disk, K, this would converge when n tends to infinity to 1 over square root of 2 pi, the integral over k of e to the minus z square. Well, I write it here. This would converge to 1 over square root of 2 pi, just to the Gaussian measure of the, I'm sorry, this would be area measure, right? Area measure. Okay. So this is the result I wanted to present today. This is joint work. This is a recent joint work with Odisole. And there are a few things I wanted to remark. The first thing is that I should say that in this result, no lacunarity assumption is needed, right? So here we have the whole sequence of iterates. Okay. The second is, well, I will not talk about the second, but we also have versions, and which are similar to versions that Zalem and Zygmunt had for lacunary series, but there is a version that we do not know how to prove. So what we don't know how to prove is a local version of the result. So here is an something open. Local versions. So this means that if we fixed a set in the circle, we do not know how to prove that these would tend to the Gaussian, right? So if what I mean is that if we fix the set on the circle, so E is fixed, a set of positive measure, of course, we do not know if this thing holds or not. And as you'll see, this, I mean, we don't know, our methods do not apply because at some point, our methods rely on complex variables arguments. So this kind of argument, typical from complex analysis, that certain integrals vanish. And well, and these are of course very nice and very beautiful, but they are also very rigid. So when we have when we restrict attention to a set of positive measure in the circle, we already do not know how to proceed. Okay. So let me skip now that. Also, I wanted to remark that well, there is a particular case which is especially interesting, which is when all the ANs are 1. If all the coefficients are 1, what we have here is, well, something like an ergodic mean, right? So when in the case where all coefficients are 1, then this variance can be easily computed, right? This is just 1, this is just 1, and here you have a geometric series. So you can really compute this sigma n, and what you get is that this sigma n squared is n times sigma squared. And sigma squared has this nice formula, right? So it really depends on the derivative of the function at the origin, right? So you should, it makes also a lot of sense, right? Because if this derivative at the origin is very close to 1, this means that f would be very close to via rotation. And in that case, of course, what you would expect is to have a very small variance, right? Okay, So now the rest of the last 15 minutes of my talk would be devoted to, well, to explain you how the Alexandrov-Clark measures enter into the game. Or at least to explain the main parts of the proof. Okay. So here, this was the result, and now to prove this central limit theorem, we need two main auxiliary results. And these two main auxiliary results are stated in my next screen. So let me first present them. Well, the main estimates are the following. So I'm going to use this notation. Whenever you have a set of indexes, so a set of positive integers, let me write by psi sub a to be the part of the sum we will consider, but restricted to the indexes in the set A. Okay. So the first auxiliary result says the following. Assume that you have two sets, A and B, of positive integers. So here I have a set A, and here I'll have a set B. Sets of positive integers, okay? And assume you have this condition, right? That the set A is at the left from the set B. Then what happens is that, well, this fantastic formula, right? It's a formula which looks like a mistake, right? It says that the integral of the product of the modulus, the square, is just the product of the integrals. Okay. So this is we understand this as a trace of independence, because remember, when you have two independent random variables, then the expected value of the product is the product of expected values. Of course, in our case, this modulus of psi sub a squared, so the modulus of square of these partial sums, these are not independent in any sense. But still it happens that the expected value, so the integral of the product, is the product of integrals. Okay. So this is the first auxiliary result, which I will discuss in a minute. And here is the second. The second is more sophisticated, but it's actually it's harder also to prove. Okay? So the second says the following. Assume that you have, well, first a notation. Let's use this notation. F to the power minus n would mean the nth iterates of the function f, and then to taking a complex conjugate. Of course, n here is a positive integer, right? Okay. So this second result tells you the following. Assume you have natural numbers, which are they are ordered from smaller to bigger, and they are in such a way that the difference between two consecutive ones is bigger than a large number q. So q will be a large number. And let epsilon j be pluses or minus 1. Then this tells you this, our estimate is that the integral of the product of all these iterates with respect to the back measure is smaller than this quantity, okay? So we should understand this in the following way. This quantity here is a correlation. Remember that some epsilon j's could be minus 1. So this means that you could have complex conjugates here, okay? And we're going to apply this when q is much more bigger than k. So the idea is to apply it when q is a number which is bigger than k. So remember that f was an inner function fixing the origin. So this means that this quantity, the derivative at the origin, is smaller than 1 because f was not a rotation, okay? So this means that you have here an exponential decay. So this second theorem tells that the correlations, the higher order correlations, decay exponentially. And this will be also very important in our proof. So my plan now is to discuss the proof of the first auxiliary result of this. This proof is very, as you see, it's very easy, and it uses Alexandrov-Clark measures. The proof of this is also use Alexandrov-Clark measure, but it's much more involved, and I'm not going to present it. Okay, so let me concentrate on this. Okay, so here is the statement, and my plan is to present, as I said, the proof. Okay. Okay, so in order to prove it, we again act in the most naive way. Okay, so remember that psi A was just a partial sum. So we need to compute the modulus square. So what we do is we just look to this, we compute the modulus square, just expanding all the terms. Okay, so what you get is something like that. Okay, so you get here the sum of the square of the modulus, and then you have the mixed terms, right? Which would give you something, this is something as the real part of this quantity here, 2 times the real part. So we do this for psi A modulus square, and we would do also it for psi B modulus square, okay? So now we need to integrate the product. So the product would consist of linear combinations, very complicated linear combinations of products of this sort. Products of guys in here against similar guys, but now in psi B. So what we would get is linear combination of guys in which appear in psi A. So N and J would be in A, one bigger than the other. And then the same thing for K and L in B, and K and L in B, and say L bigger than K. So in order to show that, what you need to prove is that the integral of this product is the product of the integrals. Once you prove this, then you put things together and you arrive to this identity here. Okay, but as I said, this again looks like an identity which should be understood as a trace of independence between this guy and this guy, right? Because it tells you that the integral of the product is the product of the integrals. And this was already, we already computed that. This was f prime of 0 to the power j minus n. Okay, so we need to start with the left-hand side and arrive to the right-hand side. So here is the argument. And here is where you will see Alexandrov-Clark measures. So we start with the left-hand side. And remember, the situation is that n is smaller than j, and k is smaller than L. Okay, so these are how the indexes are located. But now remember that by Leffner's lemma, we know that the integral of G composed with F is the same as the integral of G over the circle. So this means that I can replace this nth iterate, and here replace J by J minus N, K by K minus N, and L by L minus N. And this is what I have done here. Okay, so we arrive to this quantity. Here we have used, as I said, Leffner's lemma. And now, and here is the crucial point. Now let us consider the Alexandrov-Clark measures of J minus N. Remember that by Alexandrov disintegration theorem, dm of z is the integral of V mu alpha with respect to V mu alpha. So the Alexandrov-Clark measures, when we average them, you return to Lebesgue measure. And remember that these Alexandrov-Clark measures are concentrated in the places where this iterate has the value alpha. So this means that we are concentrating in places where this is equal to alpha. So when you write the double integral coming from this identity, coming from the Alexandrov disintegration theorem, this is going to be equal to alpha, right? Here's this alpha. And then, of course, here you would get something like fk minus j of alpha and flj minus j of alpha. And you need to integrate that. And here is what helps. What helps is that what we have got is this integral. You see in this part, you see the moment, the first moment of the measure mu alpha. And this can be very easily computed through the corresponding iterate. Now here is the formula for Alexandrov-Clark measures, right? And from this formula, you can easily compute the moments of this measure in terms of the derivative of fj minus n at the origin, okay? You just expand this in power series, right? And you arrive to this thing. So this means that this integral with respect to this integral here, we know how to compute. It's just alpha bar f prime of 0 to the power g minus n, okay? And this is very nice because this alpha bar here cancels with this alpha because alpha is unimodular. So what you get is just this quantity, which is a constant, which goes outside the integral. And the only thing which is left is this fk minus j, and this is fl minus j. So you only are left with these two quantities. And again, this by Leffner's lemma. This is just integral of fk fl bar with respect to Lebesgue measure. So this finishes the proof, right? This is what really what you needed to prove, okay? That the integral of the product, as I said, is the product of the integral. This is the first part and this is the second part, okay? So now, as you see, this is a very, a complex analysis argument. If instead of integrating over the whole circle, we would integrate over a subset of the circle, then, well, the difficulty would be that this moment would be probably hard to compute, right? Because this, in the definition of Alexandrov-Clark measures, were integrated over the whole unit circle. And this is why this local version of our result is still open. Okay, this is the first identity. And now let me just mention a couple of ideas we need in the proof. The second estimate, the second main result, I will just skip. And here is, let me just mention that, here is the main idea in the proof. The first part consists in splitting. So the idea is that we will consider this partial sum and we will split it into two parts. One part which is relevant, which are the psi case, and another part which is irrelevant, which is the eta case. And the eta case will be irrelevant because they would have very small L2 norm. And the nice thing is that the eta case are located between two different psi case. So this means that indexes in two different psi case are far away one from each other, and this gives an extra amount, say, of independence between the psi case. Once this is done, the proof uses the standard argument. To show that something turns to a Gaussian, what you need to show is that the Fourier transform of your process, say, tends to a Gaussian, right? Tends to this Gaussian. And for this, what we do is we just follow, say, standard arguments to show that this Fourier transform looks like something like that. Okay. This is going now to be a little bit fast, but I'm running out of time. So this is the main quantity you need to establish. And in this main quantity, what happens is that you see products of psi case. And when you have products of psi case, this is the moment where you will use the first identity, where those are just the products of the integrals. Okay, and then you will have also the mixed terms, and in the mixed terms, you will use the second identity, that these higher order correlations decay exponentially fast. So I think my time is over. So I thank you all for your attention. Thanks a lot.
Thank you, Artur, for wonderful lecture and wonderful course. Thank you. Any questions, comments, suggestions? I don't see anything in the chat. So if there are no questions, let's again thank Artur again for wonderful talks.